Today we are going to look at basic differentiation properties. A couple of announcements to quickly make. One is nominations for the Frascona Teaching Excellence Award are due on February 6th, which is Sunday. There's a link here if you want to put a nomination in. Second, there is a virtual spring career fair on February 8th, which is next Tuesday from 4 to 7 p.m. So again, you can scan this code in. There's some information here about how to register. I think registration is on Handshake. Okay, so today we're going to review some differentiation properties. Again, some questions around that. Those questions are going to be embedded in this video. We're going to look at an application of revenue, and we're going to look at tangent lines. So the rules for differentiation that we want to use today are as follows. If the function is a constant, so f of x equals c, where c is some constant, some number, then the derivative of f of x, f prime of x, is 0. If the function is x to the power n, where n is not 0, then the derivative, f prime of x, is n times x to the power n minus 1. So that's called the power rule. The next one, if f of x is a constant times g of x, so it's a constant times some other function, then f prime of x equals k, that constant, times the derivative of the other function, so k times g prime of x. And finally, if f of x is the sum of two functions, the derivative f prime of x is the sum of the derivatives. So if f of x equals u of x plus v of x, then f prime of x is u prime of x plus v prime of x. Now our questions today, the polling questions you're going to do today, let you practice these various rules. So we have the first poll question. And note, at the end, after you've tried the problem, you should be able to see a video which shows you how to work through the problem. So we have poll question 1, poll question 2, poll question 3, and poll question 4. Okay, our application we're interested in, and we're going to, as we go forward in class, do lots and lots of applications along these lines, is we're going to look at a price-demand equation, and we're going to think about revenue. Okay, so if a company estimates its price-demand equation to be x equals f of p, where x is the quantity demanded and p is the price, then the company's revenue is given by r of p, which is x times p, which is f of p times p. So we can write revenue as a function just of price. Now, an interpretation of the derivative is that it is the slope of the function. So if we think about the derivative of revenue with respect to price, what this means is if we have a positive slope, then increasing prices is going to increase revenues, and decreasing prices is going to decrease revenues. If we have a negative slope, then increasing prices is going to decrease revenue, and decreasing prices is going to increase revenue. So the slope or derivative of revenue is really useful for determining, if we're running this company, what we should do with our prices. Now, this interpretation, because the revenue function is not usually a linear equation, this interpretation only works for relatively small changes in price. Okay, so let's do an example. A company estimates the price-demand equation for its widgets to be p equals 20 minus 0.01x, where p is the price and x is the quantity sold. If the current price is 8, what should the company do to increase revenues? Should they increase them, decrease them, or keep them the same? Okay, so I'm going to copy our price-demand equation over to the next slide and also write down the current price just so I don't forget. So P equals 20 minus 0.01x, And I think the current price is 8. So let me just check. P is 20 minus 0.01x. The current price is 8. Okay, so remember, we want to write revenue as a function of price. That's P times X. And so we want to get rid of this X so we have a function of P. And we have a little problem here because we have P as a function of X as opposed to X as a function of P. So we're going to have to rewrite our price demand equation. We are going to, so this is sort of step 1. Step 2, we're going to take the derivative, r prime of P. So we need to figure that out. Step 3 is we're going to calculate r prime of 8. And step 4 is we're going to interpret. So we have to do a little work. Okay, so let's rewrite our equation so we can do step 1. So P equals 20 minus 0.01x. We can rewrite, bring the 0.01x to the left and the P to the right. And then we get x. We divide both sides by 0.01. So what do I get here? 20 divided by 0.01, we get 2,000. I'm just being very careful here. 2,000 minus 0.011 divided by 0.01, 100. So x minus 100p. So now we can go back to our revenue equation and we can substitute in. So revenue is as a function of price is P times X, which is 2,000 minus 100p, which we can rewrite as 2,000p minus 100p squared. Okay, so that was step 1. Let's go up here. Step 2, take the derivative. Okay, this derivative is straightforward. It's a quadratic equation here in P. So r prime of P is equal to derivative of the first term. We have a p to the power 1. Derivative of p to the power 1 is just 1. So that's 2,000 minus 100 times the derivative of p squared. The derivative of p squared is 2p. So that's minus 200p. So that was step 2. Step 3, we calculate r prime of 8, that's our current price, which is 2,000 minus 200 times 8, which of course is 1,600, so that's 400. And so the last step, of course, is to interpret. Well, first off, we can see this is a positive number. The slope is positive. So increasing prices increases revenue. And approximately, this is not an exact calculation, but approximately, if we increased prices $1, so we went from 8 to 9, we would expect revenues to increase by about $400. Now, it's not exact. If we increase prices by $10, that's probably not even close to the right answer. But maybe for $1, it's close. For half a dollar, it's again half a dollar. If we increase prices by half a dollar, we'd sort of expect revenues to increase by $200. That's a better approximation. But certainly we know that increasing prices by a little bit, and again, we have to decide what a little bit is, but increasing prices by a little bit is certainly going to increase revenues in this situation. If in step 3 we'd gotten a negative number, then increasing prices would have decreased revenue. And so we would have rather decreased prices rather than increased prices. If we've gotten 0, 0 is a little bit more confusing. If it's 0, then we don't want to change prices at all. And in fact, increasing prices or decreasing prices most likely are going to result in a small decrease in revenue. But we'll see that in a little bit later in the course. All right, poll question 5. You get to practice how to solve this problem. Last part of this class is I want to talk about the tangent line. So the tangent line at a point on a function is the line with the same slope as the function going through the point. So if my function here is in red, my tangent line is in green at the point, it looks like the point -1, 2. Okay, so the tangent line goes through the same point of the function and has the same slope. Now, we're going to use tangent lines. We're going to think about tangent lines when we're looking to approximate the function. So let's talk about how we find the tangent line. To find the tangent line, given some value for x, we want to identify the point. So the point on the function, so x equals a, that means our point is a, f of a. We take the derivative f prime of x and find the slope f prime of a at that point. And then I use the point slope version of the line. You can use whatever version you want, but point slope is nice for this because we have a point and we know the slope. Point slope version of a line, y minus y is naught equals m times x minus x naught. So the point's x naught, y naught, the slope is m. So we substitute in y minus f of a equals f prime of a times x minus a. Let me do an example. F of x equals 3x squared minus 2x plus 1. We want to find the equation of the tangent line at x equals 1. Okay, so I need to find my point. My point is going to be 1 comma f of 1. So let's find f of 1 here. F of 1 equals 3 times 1 squared minus 2 times 1 plus 1. So that's 3 minus 2 plus 1. 3 minus 2 is 1, plus 1 is 2. So that's 2. So our point is 1 comma 2. We've got to find the slope. Take the derivative to find the slope. F prime of x equals 3 times the derivative of x squared. So that's 3 times 2x, which is 6x, minus 2 times the derivative of x. X is just x to the 1. We use the power rule. We get the 1 down, so that's 1 times x to the 0, which is 1. So the derivative of x is just 1, and so we get minus 2. We need to find the derivative at our point. Plug in a 1. 6 minus 2 equals 4. Again, point slope version of a line. Y minus y 0 equals m times x minus x 0. And so we get y minus 2 equals 4 times x minus 1. Again, generally we like to have the y on one side, and we get 4 times x minus 1 plus 2. And that's it. That's our equation of the tangent line. Again, you can practice, and that's it for our lecture today.